Okay, it is 10 a.m. and I actually 1 minute past 10 a.m. now, DC time. So I will get started. Welcome back to week 3 of development research in practice. You met me last week, but if anyone skipped week 2, my name is Christopher Bjerkfjord, and I'm a data science consultant at Time Analytics. This week we will be covering chapter 3, establishing a measurement framework. However, before I get into any of the content of the day, I will start with some housekeeping notes. So again, all the links related to the course material, quizzes, reading lists, application questions, all of them are linked in this document that you find by entering the URL bit.ly/drip-overview. And I think Avnish will post the link in the chat right now. We also share this in the beginning of every week in the Slack channel. So please look for them there. But if there's something you don't find, you can always ask us. But always start by looking there. Please keep your participant ID safe and make sure that you're using the correct ID when you submit your quizzes. I think that we have had some people using their incorrect ID, and we can fix that. But to make sure that you get your own score, make sure to don't share your ID with other people, and make sure that you're using the correct ID when you're submitting your quizzes. And all quizzes have one common deadline. That is September 1st, 11:59 p.m. Eastern Daylight Time. So all quizzes, no matter which week, no matter which chapter, they all have that one same deadline. Okay, so in chapter 3, we're still in the design segment at the top of the diagram to the right. So that and this diagram describes the data work lifecycle we have had in mind when writing this book. This means that most of the tasks in chapter 3 should be done before you start acquiring any of the data you will use in this project. In the first 2 sections of this chapter, we discuss how you plan what data you will need to be able to answer your research question using the research design that your team has chosen, as well as how you document these data needs. Since the data you will need is likely to come from more than one data source, you should also at this time, well before you have acquired any data from these different sources, also make sure that the data from different sources can accurately be linked together. The tool that we recommend to do exactly these things is the data map. And the first section of this chapter introduced the Time Analytics data map template, and that is what we will spend most of our time on today in this presentation. The second section of chapter 3 gives example of different research design should be expressed in the data map, but most of the things I want to say related to section 2, I will mix in when I'm talking about the data map from section 1. And in the third section, we will discuss the practices required when using random processes to create research variables and how to make those random processes reproducible. Before we get into any of the sections, I want to talk about a topic that's central to this chapter, and that is research variables and measurement variables. So I want to spend some time discussing these definitions. These are definitions that we introduce in this book. And on a high level, these 2 types of variables can be distinguished by saying that measurement variables measure the topic in focus in your research question, while the research design variables maps the observations to your research design. Let's use an example to explain this. For example, in an agriculture research project studying farm output, let's say that we have a data point saying that a farmer grows 100 kilos of potato. This data point is a measurement variable, as is an observation of the output studied in a research question. However, in order for us to be able to say something scientifically about what makes a farmer grow a lot or a little potato, we need variables that map this farmer to our research design. So in an impact evaluation, we might, for example, evaluate a program's effect on increasing potato yields. A common way to evaluate that program is to randomly select a group of farmers to receive that program and have the other farmers as a control group. If we then measure potato yields and after the program is completed for both of the groups, we can compare these groups and say something about the effectiveness of the program. That's the theory. But to apply that theory in our data work, we need a variable that says which farmer received the treatment and which farmers were controlled, and then we compare those groups. And this variable that indicates which is farmer is a treatment and which farmer is a control is a very typical example of a research variable. But then we can also start asking, like, how do we know that these differences in groups was indeed due to one group being offered a program? The farmer that was offered a program might have had a higher yield of potato in the first place. One way to make sure that differences after the program is indeed, or differences before the program is not the reason why we see differences after the program, could be that we also collect data before the program starts. But to do that, we need more research variables. We need an ID variable to know which data point before and after the program belonged to the same farmer. And we need to know which data point was before and which one was after. So we need a time variable that indicates the time of observation. These are also research variables as they both serve a function, they more serve a functionality in a data work rather than saying something about the context that we study. The functionality research variables serve is very important to our research, and they therefore require extra care. This extra care is a lot of what today's presentation is about. But I hope that you now have an intuition for what's the difference between a measurement variable that says something about the context we study and the research variables that serve a functionality, so we can apply a research design to that, to our measurement variable, the data in our measurement variable, so we scientifically can say something about the context that we study. First section, documenting data needs. So in the motivation video for this week, I mentioned oral tradition. So oral tradition is the practice of passing on knowledge from one generation to the next. And the importance of oral tradition for human culture cannot be stressed enough. But as I said in the motivation video, it is simply not exact enough for a modern research team to rely on. What is oral tradition in the context of research? Why do I use this comparison? So it would be when like a senior research only use meetings or mail to communicate their vision for the data work to the team. Even this email is not exactly oral communication, but the issue that we're getting to here is that most modern research projects runs over several years. And that means the research team members will join and leave during the duration of the project. And just as a future team member cannot know what was said in a meeting that happened before they joined, they also have no way to be included on an email that was sent before they joined. So that's why we will still categorize both speaking in meetings and email as kind of like an oral tradition. And if you rely on oral tradition, that means that when a new person joins a team, their understanding of the project relies on someone repeating verbal communications from a previous meeting or forwarding emails. Neither of these two practices are exact enough for data work. Something will be lost in that translation, or an old email will be forgot to be sent forward to the new member. So instead, these decisions should be documented in a data map. And in this book, we're introducing the Diamond Analytics data map template. A template we think is the most efficient way to document and communicate about data requirements. The same information that goes into this data map can be described in a text in a regular document. However, using the table, datasets, and flowcharts that we are about to discuss in the next few slides, in our experience, that's both the most efficient way to communicate this information and the easiest way to spot errors or missing information. While this data map template is new, each component of it has been used in DIME projects before. What is new about this template is that we have stipulated guidelines so these three components fits well together, so that the benefit of using them together is greater than the sum of each component's individual benefit. In the data map, the three components that we have is a data linkage table that lists all the original data set and the metadata of those data sets. The master data sets includes all the research variables for all observations, and the data flow chart, which shows how to create an analysis data set. You will learn a lot about the data needs for your project while developing the data map. You might think that you can just think of everything in the data project, but our experience is that you always learn something new by developing a data map. So it's important that you start doing this before you're acquiring any data. As once the data is acquired, it is costly or sometimes even impossible to having to go back to the data source and add data you did not realize that you needed before you had created your data map. So create a data map as early as possible in your project before you acquire any data. The first component of the data map is the data linkage table. In a data linkage table, you should list all original data sets. By original data sets, we mean data that the research team will acquire in its original form. This can be like the data collected using household surveys, data scraped from the internet, or secondary data received from a partner organization. But original data in this context mean the data set exactly how the research team initially received it. And the example of the data linkage table you see on the screen can be downloaded using the link to OSF that you see on the bottom of the screen. You can use this as a template. You can, maybe the information is small, you can't really see, you can download it there and you will see it in a bigger font on your screen. But you can also use it as a template for when you apply this to your project. The most important purpose of the data linkage table is to make sure that data acquired from multiple sources can be linked to each other. This is done by indicating the unit observation and making sure the same project ID is used for the same unit observation. See column D and E in this table, where in D, the unit of observation is expressed in plain English, and E is and E indicates what the variable with a project ID for that unit observation will be called. All data sets with the same unit observation can be linked in a one-to-one merge. One-to-one merge means that no one row in one data set is matched with two or more rows in the other data set. An example of this would be to merge community listing data set that you see in this table with the baseline prices from those communities. So in these communities, you will have one community that says 1, 2, 3, maybe that's the ID. And then you will have that ID in the community listing, and it will be exactly a one match of that, the prices in the baseline prices. So both of these unit observations have community, and you will find community 1, 2, 3 in both of them, and there's a one-to-one row match there. But data sets with the same unit observations can also be appending. Appending data sets, that means that you're combining them by adding more rows, meaning adding more observations. So if you have community listing from one region, and then you have community listing from another region, both of them have the same community ID, like both of them have the same unity observation, but have different communities. You can append them to each other, so you add more rows, adding more observation. That is possible only if you have the same unit of observations. And when you merge two data sets, what you do there instead, you add more columns to existing observations. So that's the difference between appending and merging. That doesn't mean that you, in every single case where you have the same unit observation, it makes sense to merge or append them. It's just saying that if it's not the same unit observation, you may never append, and you will not be able to do a one-to-one merging. If one row in a data set will be matched with during a merge will be matched with multiple rows, that will be a one-to-many merge. An example of this would be merging the baseline data set with a baseline price data set with a farmer baseline data, as the price data set is on community level, where all farmers in that community will be matched with that community. So the prices for one community is merged with all the farmers living in that community. Column G and H in this data linkage table example shows which other unit observation each data set can be merged one-to-many and many-to-one to. This might seem trivial in this small example, but it's a good practice, as you should at this point plan to make sure that all your farmer level data has the household HHID, household ID variable, And then all community level data has the community ID variable. And if you don't, you need to start planning for how you will match these data sets to those IDs. For example, if you receive a data set from a government partner, they will not have your project IDs. So you need to, at this point, plan how do you have exactly the IDs that you use in the project IDs in column E, so you know that you can link the data based on that ID. And you should also make sure that data sets can be linked if they have the same unit observation, and they can link if they have any community ID. If you have a data set and they list other IDs in column G and H, the one-to-many and the many-to-one merges, that means that you can also link those data sets with any data sets that have that unit observation. So before you continue, you should make sure that if you have a data set that need to be matched, at some point will need to be linked with another data set. You need to make sure that they either have the same unit observation or the other unit observation is in either the G or H column. It can also be the case that you have to first merge one level. Let's say you have patient data and you first need to merge it to doctor data before you then merge that to community level or clinic data, so that you have, it could also be an indirect way to link, but you need to make sure that there is a direct or an indirect link through the data linkage table if you know that those data sets need to be combined at some point in the future during this project. The data linkage table is also a great place to list where original data files are stored when they're backed up. Last week, we said that if you create all derivative data sets and research output with version-controlled reproducible code, starting from your original data sets, then all your derivative data set and outputs are also versions controlled. Since the starting point in that statement that I just said is the original data, it's important that we know where those files are backed up. We will talk more next week about how to backing up data, but the data linkage table would be the place where you list where the data is backed up. So there's never any confusion or the collective memory of the team forgets where did we back up this data. Again, this is a template, and if anyone starts using this, we would love to hear what modifications you're doing or what you think are other nice things to add to the data linkage table. The second component of the data map is the master data sets. The master data sets is where you store all research variables for all observations. We have already talked about some research variables such as product IDs, alternative IDs, treatment assignment, etc. But it also includes identifying information, as this is the data set you would use if you had to merge product ID to a data sets that only use names as identifiers. That's an example that we'll cover on the next slide. You should create one master data set for each unit of observations that used in any significant research activity. Examples of significant research activities are sampling, data collection, treatment assignment, analysis. In many projects, the unit of observation is the same for all of those activities, but it's definitely possible that you can use different units of observation for this. Maybe you collect data on farmer level, but your analysis is on community level. Then you will need to have a master data set for each of them. You also, and then you can have data collection from many different sources and using different unit observations. And we saw in the data linkage table on the last slide that it was common there was different unit observations. So you will need a master data set for each of them as well. You should also include all observations the project ever encounters in for all units or all observations on this unit of observations in this master data set. Even if you decide that they are not in your sample, you should still include them, because knowing that a person exists and is not a part of your project is also useful information to you. To give an example, let's say at the master data set that you see in the screen is from a project where some farmers were sampled, and half of those farmers sampled were then offered a training, and the other half was offered a placebo. And what they were offered in the treatment was to attend a training, and the purpose of this research project is to evaluate the effect of this training. In the master data set, we have the variable treated that you can see that indicates who were offered the training. You see in sample, who we sampled to be a part of our project. And you also see the variable attended training for people who attended the training. Take for example, Sid Fraser in this data set, the third observation you see from the top. They were not in the sample, but they still attended the training, despite that was not according to a research design. Something like this is common, and most often it's just due to the fact that perhaps the teacher of this training might not know that what they're doing is a part of a research project, or they might be aware of this, but they don't know how important it is to a research design and to the validity of the research result that is implemented according to the intended plan. But this is common, and this is the reason why we need monitoring data. So that's why we have this list of attending the training, because just because we offered someone this training, we don't know if they're going to attend a training. And in this case, the monitoring data is likely to be something like a handwritten list of attendees. And Sid Fraser's name would be on that list. Had we not included Sid in our master data set, then we would not have had a perfect match on that name. And when we don't have a perfect name on a match, there's no way for us to know, is Sid really this person's name, or is this a typo, and this actually is someone else in our master data set? Maybe we can start looking for other people in this master data set with a different name. And you see on the row below, you have someone Didi Fraser. They might be related. So it's a high risk had we not included Sid Fraser in this master data set. It's a higher risk that we would have think that Sid was a typo, and we would then have indicated Didi as have attended the training, because that would have made sense, because Didi was offered the training even though Didi didn't show up. Then we would have incorrectly included Didi in our analysis as if they had attended the training, and that could skew our results. Some mistakes like this are always inevitable, but by including all observations we encounter, not just those we intend to include in our study, we are much less likely to make mistakes like this. So knowing that someone exists but is not included in our study is useful information to the team. And that's why we should include everyone in our master data sets. To build on that, the master data sets should be seen as the authoritative data sets for all research variables. That means that if there is a data set to which a research variable needs to be merged, it should always be merged directly from the master data set, even if that research variable exists, for example, in an analysis data set. One reason for this is to avoid the case with Sid and Didi on the last slide. It is also to avoid that you play a game of telephone with the research variables. The game of telephone is a kid's game, but that exists in America, but I also know that it exists in Europe. But if one of you doesn't know it, I just super quickly explain it. So a game of telephone is where person A whispers to send a sentence to person B. Person B then whispers the same sentence to person C, and C to D and D to E and so forth around the room until the last person have had the sentence whispered to them. And then they say the sentence out loud. And then person A says if that was exactly what they said in the beginning, or if the sentence had been modified. And almost always in this game, in this kids game, the sentence is modified. This is the same with your research variables. So if you want to add treatment status to a data set that you have, or monitor indicator or something like that, you should always do it from the master data set. Because if you would merge the monitoring indicator from the monitoring data to one survey data, to then another survey data, and then from that survey data to analysis data set, you're playing the game of telephone with your research variables. Eventually, some modification will have that then transpire through the whole for all the data sets of your project, and you will have incorrect research variables, which is a big problem because they serve such an important need as functionality in your project. So if you see in the image, you have a master data set with project ID, and then this is similar to what would happen in the Sid and Didi example. And we have identified monitoring data without product IDs, and we have identified survey data with product IDs. If we need to combine the monitoring data and the survey data, both of them identified, they both have names, we can try to match them on their names. However, since the survey data only includes the people in our sample, it's much better that we first merge the monitoring indicator to the master data set, because the master data set includes everyone, also people not in our sample. Here we merge on names. That is very error prone because of typos, because maybe we have to read handwriting at some point. So this is very error prone, but we solve this once and for all. So we add the monitoring indicator to the master data set. And then after the merge on names, you see in this diagram, we have the master data sets with monitoring indicators and with project IDs. That means that the next merge, we merge on project IDs with the survey data, is a super simple, super straightforward merge on the project IDs. So we solve all the issues when we merge data sets without the project ID to the master data sets. And then we have an accurate and error-proof way to merge all those data sets with other data sets using the project ID. And in the end here, we have the analysis data with the monitor indicators. So, and since the master data set is likely to have identifying data, it needs to be encrypted at all times. If you need frequent access to your research variables other than the identifying information, for example, the monitoring indicator, then you can create a de-identified version of the master data sets that you can keep unencrypted. Final point about the master data sets: when should you create them? As everything that I said this week and last week, obviously, we recommend that you create the data set before you acquire data. But how can you do that when you do not have any data to populate the master data set with? Well, you can list which unit observations you need data sets for and what research variables they will need to include. Then you still have the information about which master data sets you have and what variables do we need, even though that you don't have the data points for those variables yet. Third component of the data map. The third component of the data map is the data flow chart. To create a data flow chart, start by identifying all the analysis data sets that you will need to answer your research questions. The next task is to add them to one or to add all your analysis data set to one or several data flow charts. If two analysis data sets are created in a similar way, or one analysis data set is created directly from another, then they can share the same flow chart. There's no hard rules that it need to be one flow chart per analysis data sets. The only rule is that each analysis data set should be in a flow chart. This is the example that's used in a case study in their book, and the analysis data set they needed was the platform is indicated in the screen. So this is the first thing. So you kind of start from the right and go through. You start from the right in this data flow charts. You're likely to need several of these, but we'll just use this one example. In the next step, you list all the starting point data sets that will be used to create this analysis data sets. You're only allowed to have either master data sets or original data sets listed in the data linkage table as starting points in the data flow charts. This is because the original data sets are the authoritative sources of measurement variables, and the master data sets are the authoritative sources of research variables. And by only allowing these starting points, you make sure that your data flow charts only starts an authoritative source for that data. And this might be the place when you realize you need data that you have forgot to include in the data linkage table. This is, again, why we want to do this before the team starts to acquire data, so you can make changes to the data linkage table and make sure that all data you will need will be acquired before it's too late to do so, or be too costly to do so. And the final step when creating a data flow chart is to include all the operations needed to turn the regional data sets and the master data sets into the analysis data sets you will need. The operations you must include, and then all these operations that you must include are operations that either combine two or more data sets into one data set, or any operation where the unit of observation changes, such as aggregating values, reshaping the data from long to wide, etc. Example of operations that does not need to be included are like addressing outliers, imputing missing values, standardized units, etc., as they only modify single data points. You may, of course, include more operations that those we say are required if you think that better communicates what the intent is, or what the thinking behind these processes are. But if you were to include all of them, this data flow chart would be way too cluttered. And again, this is another point where you were likely to realize there is something you forgot to include in either your master data set or your data linkage table. And we want you to create all of these three components as an iterative process, where you go back and forth between the different components until you have a data map that makes perfect sense, where all the three components makes perfect sense. And this process could also be a step where you where you can identify extra complex, extra error-prone processes that you have to be extra careful with, and you have to try to think what could go wrong. An example of this would be that observations are incorrectly dropped as they were not matched successfully. An extra care in this context would mean that you include a test in your code to make sure that the number of observation is as expected after operation. And you can see on the data flowchart example on the screen, there's also a lot of bullet points saying what is expected. So it's expected, if it's expected that all rows should match, or it's expected that not some rows is not going to match, it's some going to be dropped. Like all of this can be expressed in the data flowchart to make sure that especially error-prone steps are done correctly. And then once you have all these three components that we talked about in the last couple of slides, you have your data map and you have a tool that will help your research team communicate about the research activities and execute all these research activities with a common understanding and a shared intent. So the time that you put into making this data map will easily pay off in a much smoother and quicker and efficient data work and a much higher quality research outputs in the end. And while the data map should be created before you start your data work, it should also be seen as a living document that you keep updating as you learn more about the context you're researching. It's very common that when we study something, that this is a topic that haven't been studied in the context where we're studying it before, and we might learn new things that we need to include in our research, or we can come up with additional research questions we want to be answered. So if you do this and if you include those steps in your project, then it's perfectly fine to update your data map as you go. But as we said many times, it's much better to do this before you start acquiring any data. I will bring up the Q&A to see if there's any. The data linkage table and data flow shall have a lot of similarities. What could be the cardinal difference between the two? I see one Q&A that's not answered. So the data linkage table you can see one way to explain this: the data linkage table is empirical, like this is the meta information about these data sets, while the data flow chart is more normative. This is what we want to do with these original data sets. So the data linkage table have just empirical metadata. These data sets have these characteristics and they are like that. And then the data flow chart would then see like our intention with these original data sets and master data sets is to combine them like this. That's not an objective truth, it's a normative intention. And in order to create this analysis data set. And I think that like in the data flow chart, if you have a huge whiteboard, maybe you can fit all this information that's listed in the data linkage table as well in your data flow chart, where it's backed up and all this other information. But it's probably not a good practice to do anyway, because most likely you will have to use data flow chart, and then you would have to list that metadata about the original data sets in multiple locations. Because each original data set and each master data set can be used in multiple data flow charts, but we don't want to create that redundancy of expressing the same information in multiple places. Thank you. I will now move on to translating research design into data needs, the second chapter. A lot of the things that a lot of the information in this chapter, I already have blended in when I talked about the data map, especially they talk about the research variable. So I will cover this section quite briefly. But one thing that I want to say before getting into this, that the scope of this book focuses on the practical aspect of data work. That is what in practice in the book's title referred to. So there are many great books already written on the statistics, economic theory, and math of the research design that we commonly use in our field by people that have specialized in exactly that. The four of us that wrote this book, we're all trained in those things, but we have specialized in the practical aspects of data work. And this is what we identified there was no good resource for, or at least we didn't think there was a good resource for this. And so that is what this book is about. So if you have come to this training to learn a lot about statistics and theory, unfortunately, this is not the scope of this training of the book, but at the same time, we have included details about this in Appendix C. And the book, since it's related to those topics, both the book and the reading list links to great resources on topics outside the scope of this book. So instead of digging into all the infinite number of possible research design there are, and because there's no way for me that I could just sit and list all the data needs for them, I still want to use, instead, I want to use our poll everywhere to do a little bit exercise for this section instead. So in the book, as you've read this chapter before today's session, we have examples of data needs in research design commonly used in impact evaluation. And we use mostly impact research design common in impact evaluation because that is what the DIME department specializes in. If you do not work on impact evaluation and other research designs, and other research designs are more important to your work, we still hope that the examples provided in the book still gives you a good idea on how to identify what research variables your research design requires. So instead of listing more examples than those we give in a book, I will use our poll everywhere tool for you to be able to test your ability to identify research variables based on the research design examples I will give in the next two slides. So on the polls on the following slides, use these four categories when you try to think about which research variables needed in the examples that I'm about to give. So these four categories to compare groups, usually when we compare groups in order to see what's the difference in a group, and then we can induct something from that. So the treatment and control or legibility. We need to link data sets across different sources. We need project IDs for that. Repeated data collections. If you're going to collect data multiple times, we need identifiers, contact information, and location. And if the treatment is something that we don't know if the people will actually take up, will actually use what's offered to them, we also need some monitoring data. So go to the poll everywhere, and I'm sure someone's going to publish that in the link, and provide examples of research variables on this design. 1,000 people are included in a medical study where 50% of them are randomly assigned to receive a vaccine and the other 50% receives a placebo. Health data is collected on all 1,000 people at the time of the vaccination and 1 year later. Give examples of research design variables that you would expect. And also there's a lot of unknowns here. This is like a very brief description of a research project, but I think that you should be able to guess some of them. I don't see. Okay, perfect. I was afraid for a second that I hadn't activated this poll. Treatment, absolutely. IDs, patient IDs is absolutely another thing we need to keep track of these people. HHID, that usually indicates a household ID. I think for this would be more better to have a patient ID than calling it HHID. HH in survey data tend to indicate households. Also, it splits the words. Age, gender, race. That could be that if that is needed to indicate who each person is in this study. That's like sometimes if you're in a context where people have a lot of similar names, you might have to use age to also identify who someone is. However, when we collect health data, it's typically very important to collect data on age, gender, and race, but we don't use that. We don't always use that to identify people across time. So then that more likely be a measurement variable rather than a research variable. And then if they receive the vaccine, that's a monitoring data. And then I'm not picking up more kind of things. But anything that's related to the health data is measurements variables. because that is something that we study, the context we're studying, the health of these people. But other examples are research variables. The most typical for this one is the treatment status. One more similar question: 50,000 students take a test. Anyone scoring less than 60% is offered a month-long training. All students takes a similar test after 3 months. The efficiency of the training is evaluated by comparing students who scored 59% with those who scored 60%. And in this case, this is a regression discontinuity study. We mentioned that in the book, but if you don't remember that, just quickly let me explain. So if we have students that score 59% and students that score 60%, those results are so similar that we expect those students to be very similar. The only difference is this tiny difference if they scored 59% or 60%. That is the only pre-existing difference that they have. But the one thing we introduce as a part of our research is that those that received 59% received a training. So then, since before this study, we expect the 59 and 60% students to be similar, and after the training, the only difference then is that someone has addressed the training. So the only difference in the test result after 3 months would be the training. So test scores is important here because we need to know the eligibility. And if they actually attended the training is another important research variable. I do see something about health and vaccination. I think that's probably a result that's still coming in from the last slide. So the most important here, and we need to know which students had the score of 59 and which had the 60. So that's that eligibility indicator, but the test score as well. Because some people maybe had only 20% on the test, and they're eligible for the training, but we don't expect them to be similar to someone who received 60% of the test. So we need the test score, the eligibility, and we need IDs to track them across time. Those are examples. And then depending on the details of the study, you would have other examples as well. I'm bringing up the Q&A before I go into chapter 3. Any software to use to record emails and meetings in an organized way. There's, if you would just have, I won't have a good example to your question, and I think what I'm going to talk about is the reason why I think that. If you would have something that's fully automated, they would record all the information said in emails and software, or emails and meetings, and then that would be too much information. And then otherwise, what people would do, you can make notes from emails and meetings and summarize and synthesize that information somewhere. And so either if it's automatic, it will just simply be too much information, so it's not useful. So human have to go through and synthesize and summarize that information somehow. Where would you summarize that information? If it is about your data needs and the data work, we think the data map is the best place to make note of that. Then there might be other decisions that you make, like which survey firm to hire, which contracts, what to do, those more project organization aspects. Those might not fit in the data map, and you would have to make note of them anywhere. So I have not seen some new AI machine learning software that can synthesize what human says. This is the most important part. I think there is a manual process that's required to this. So test score, wouldn't that be a measurement variable? Eloisa is typing an answer, but I can also say there is some gray zone between what is a measurement variable and what is a research variable. But if it carries a functionality of translating the observation, the research design to your observations, then it's always a research variable. Some of these could be a little bit of both. But the important point here is that the research variables carry such an important functionality in your research that if it is also a research variable, like mostly a research variable, but also a little bit of a measurement variable, you should still treat it as important as a research variable, because a small error in a research variable can completely flip how we treat this observation in our research, but a small error in a measurement variable is usually averaged out when we look on the average and the sum of the full groups. So if it is a little bit of both, treat it still as a research variable. Section 3, creating research design variables through randomization. This section discusses how we implement random processes when writing code for reproducible research. Random processes are commonly used to create research variables. For example, random sampling and random treatment assignments are used to generate groups that are expected to be either statistically similar among the groups or be statistically similar to the general population. As described in chapter 1 2 weeks ago, reproducibility is very important for research transparency and research credibility. If your code does not reproduce the same result as the report of your paper, then a lot of people won't trust those results. So that's why reproducibility is very important. In Dynalytics, we review and make sure that all code used to create results in Dyne publications are reproducible before those publications are made public. In addition to that, we also have quarterly code peer reviews when RAs exchange code with each other and review each other's code. And when they do that, reproducibility is one of the things that they test for. And the number one reason for why project results cannot be reproduced in either of these reviews is that a random process is not implemented such that it is reproducible. And to make random process reproducible when you write code, you need to follow some very exact steps. These steps tend to be quite similar between different programming languages, but they can have small and very important differences as the reproducible random process can have been implemented slightly differently in these different languages. The book and this presentation on the next slide will cover how this is done in Stata. And if you're using another language than Stata, you need to research how it's done in your language, but the principles tend to be same, but how you implement it can have a small difference. So, but since the principle is still the same, even if you never use Stata, I think the next slide will be useful for you. However, before I go to the next slide, I want to cover 3 things to consider related to creating research variables using random processes. Again, this book is not about statistics, so this book or my presentation right now won't cover this in details, but these 3 considerations, I think it's still useful to know if you're about to create research variable using random processes. And first, a comparison. For example, if you roll 2 dice, and the sum of those 2 dice, and then sum the number of dots on those 2 dice, you're expected to get on an average on 7. But you don't know that you will get 7 each time. Most of the times you will get 7 or close to 7, but sometimes you can get 12 or 2. So if you expected a 7 outcome, you can sometimes be unlucky and get a 2 or a 12. On average, this becomes rarer the more times you roll the dice. So if you do something a lot of times, it's then likely that your result will be close to 7 on average. Something similar can happen when we use the random processes in code, and that is what these 3 considerations are about. So if we assign different groups into different, if we assign a sample into different treatment groups, we need to test that afterwards on key statistics, key characteristics, these 2 groups are indeed similar. This is done in a balance test. Because you can be unlucky and all the more prosperous individuals ends up in the treatment group and then all poorer individuals receive in a control group. And then that will drive the result rather than the treatment that you're implementing. Random inference, this is a way to test what is the likelihood that the difference observed in groups is due to an unlucky randomization. This is a very good thing to know. And if you see that the likelihood is too high, you might have to increase your sample size or change your research design in some other way. And also regarding to sample sizes, you need to think about and calculate, and the book gives a few examples on how you implement all of these 3, like how big of a random sample is needed to detect how big of an effect. So this is just to mention quickly that randomization is not a silver bullet that never can go wrong. It's a great tool, but we have to be conscious about that it could go wrong and we need to test for that. So reproducible randomization is data. We have a link in the readings to a presentation that goes into this in more detail, but this is true for all languages. Generating random numbers is too slow. Generating random numbers on the level of randomization that we need, I think that's the word to use here, randomization that we need in order to say, like, if we generate 10,000 numbers, they should indeed be random. Creating something like that is too slow if you do it in real time. So therefore, Stata and all other programming languages predefined very long list of random numbers. So in Stata, to make this randomization this random process replicable, we need 3 steps. It's version, because different versions of Stata could have different predefined very long list of random numbers. So Stata has statisticians that analyzes this list, and if they see some non-random pattern in this long list, for next version they will have updated this to remove that non-random pattern in the list. But to make sure that your code is reproducible, you have to indicate to whoever will reproduce your code which version to use, and we in order for the results to be reproducible. And we recommend using our command IEvolStart because that's one of the things that it does. It sets the version so that in all random processes, the same list of predefined list of random numbers will be used. Then you need to sort the data, because the first item in that list will go to the first observation in your data set. So if the sort order is different between these times, then it's different observations will get the first number in the list. So in order to make this reproducible, so each observation always get the same random number, you have to make sure that the data is sorted the same way. That also means that it has to be exactly the same observations, because if you would add or remove observation, the sort order is no longer the same. If we would start on the first number of that list every single time, we would use the same random numbers over and over and over again, and that creates a pattern. So we have to randomize where on this list that we start each time. We do that by setting the seed. So that means that we can start in the beginning, in the middle, or in the end, or anywhere of this billions and billions of items long list. So every time by randomizing the seed, we randomize the starting point of this random process. I'm going to see if there are questions. I see 2 questions. I see Luisa and Ben is typing answers to this. Stop typing if you want me to answer, and I read them quickly. Oh, so if you find that the treatment groups are not balanced after you run the randomization, this is tricky. If you keep randomizing until you find balance, this could be seen as like data p-hacking or data mining that Ben talked about 2 weeks ago, because if you rerun something multiple times, it could be like you are running the randomization until you get a result that you get. I won't get in. I'm not an expert on exactly how to deal with this. I'm just going to mention a few things, and then you will have to do your own research, or like this is what you will learn if you do a microeconomics PhD. I guess I haven't done one, but you can then these characteristics where you don't find balance, you can include them as controls in all your regression. So whatever imbalance that characteristic created is then controlled for an analysis. However, this is a difficult topic. How to do this? It's most of the times, if your sample sizes are big, you will find balance, and it will not be an issue. If you do not find balance, you need to talk to either have a PhD in economics to know what to do with this, or in microeconomics, or talk to someone that has. This is difficult. It's quite tricky to, and people will always question something like that. So, but big sample sizes tend to make sure that we get closer and closer to get the 7 and get further away from the 2 and the 12 to keep using the dice. So keep asking questions. Here, this is the research team task division. As usual, the principal and the investigator is in charge of that the data map is created, and make sure that this correctly communicate their expectations, their vision, their intent about what all the data products will be made. Because if a PI doesn't have an efficient way to communicate it to the full team, and then the team has to learn this piecemeal by piecemeal, and there's no way to come back to and make sure that you update your information based on what the intent is of the lead researcher, it will be inefficient. You will have to come and ask questions a lot of times, or mistakes is likely to happen. And then the principal investigators typically have a PhD in microeconomics, so they're the person who is the best suited to answer these questions. What research design variables do we need? What characteristics do we need? And then if we have treatment assignment and there is imbalance in at least one characteristics, what do we need to do? That is typically a research responsibility of the principal investigator. But then the research assistant is typically the one that creates the data map for all the requirements, and then also have to report to the PI whenever it's like, hey, I run into this situation, this is not covered in the data map, how would we do this? And then update the data map to cover that context as well. And then make sure that all the data requirements, all the data required by the research variables is indeed in data map. The RA will spend much more time looking at these documents than the principal investor do. They usually like sign off, but then it's up to the RA to report when something seems to be missing. I have two. So I see Ben is explaining a measurement variable is something that actually I start reading about while Ben can write this one. Thanks for referring. In my opinion, getting balanced group hinges on assumption that. Yeah, I think that whoever wrote that answer probably have a PhD in economics and might be better suited to answer that question. So that's also like if this is a key character, if this is a character, so usually you include in a balance table more characteristics than you actually like. You include the characteristics you have data on, and then you can also ask yourself, is this a characteristic that's actually likely? How likely is it that this characteristic actually will affect the output that we study in any way? How would a data map look for qualitative data? I'm not an expert in qualitative data. But I don't see a problem for how to. It depends on you synthesize the qualitative data. But the only way I can express this is if you in any way from your qualitative data create an indicator that then you will use in your quantitative analysis, and that's what I'm specialized in, and that's the only thing I should sit and speak in a webinar with a lot of people on. So the qualitative activity can be seen as a data source that creates an indicator. So then they will be listed in the data linkage table, and that can also be a starting point in the data flow chart. So I won't speak about the process of qualitative data, but if any output and from the qualitative data is to be used in quantitative analysis, then that should be listed as a source in the data linkage table. How does the seed length affect the reproducibility in the sample? So in the book, we're saying we should use a seed of at least 6 digits. You can use many more digits, but it doesn't directly affect something. But if you give if you use a seed that's very short, just one number or two numbers or something like that, so if you use like 17, it's very likely that you over the course of your career or like other people in your team or something like that will use exactly the same seed over and over again. Then you will repeat the same random sequence over and over and over again, and that creates a pattern that's no longer random. But if you use at least 6 digits, that's what we're suggesting in the book, then it's very unlikely that you will, and you randomize that those 6 digits, you use a new 6 digit every single time, it's very unlikely that you will come back and use the same random sequence ever again. That's the reason. There's no like direct relation like 6 digits creates this in the seed. There's no such thing. It's just to guarantee that you're very unlikely to reuse the same seed a second time. And even if you do it one time out of a million, that's what it becomes. 6 digits is almost a million. It's a million if you include 0.0000. Then it's a chance of 1 in a million that you're using the same seed a second time, and that is okay. We are reaching 11 a.m. DC time. I also want to show these, but you have the full list of application questions, also shared on OSF. I'm happy to stay a few more minutes if there are more questions. And if Luisa or Ben and Maria who answered questions, if there was one question that came up multiple times, I'm happy to repeat the answer to that. Otherwise, I'll wait here and drink some water and wait for more questions. I'm still going to be here for another 5 minutes, but if there's no other questions, you can start leaving the webinar. But I will be here for another 4 minutes. You're welcome, anonymous attendee. So there was this question. I think someone must have closed the question. So I don't really understand animal studies example, but I think that the difference between experimental and quasi-experimental, I can talk about the difference between the two, and I don't know exactly how to go into the details that or the context that you gave. But experimental designs is when the research team induce some kind of variation into the sample, into the population. For example, that we assign like a treatment. We assign that this group receives the treatment and this group does not receive the treatment. So we control something, and then we create a difference in an otherwise statistical similar group. The research team creates that. That's an experimental design. Quasi-experimental design is that where there is a group that is statistically similar, but somehow this has been split into two groups by something the research team does not control. For example, in the example that I have about the 50,000 students that took the test, their test score is not something that the research team decides. This is just a cutoff that exists. We're not in control of this. We can control exactly the level, but we're not in control over which students ends up on which side of that cutoff. So that's quasi-experimental because we are using something that we were not in control over to say we have these two groups that are similar, but there's one difference between those two groups, and that's the difference we want to study. So in this student example, the one difference is that the students that scored 59% or receives the training, but the students that score 60% that we expect to be statistically similar to the first group did not receive. So the only difference between those two groups is the training, but we did not decide who got the training. So that's an example of a quasi-experimental. So it's like, are you creating these two groups, or did something in the real world create these two groups? That's the difference between experimental and quasi-experimental designs. Okay, I'll give a few more seconds for a very last question. Otherwise, I will end this webinar. Thank you very much, and I hope you enjoy reading for next week as well. Thank you.